this module. You will learn about Dalton's law of partial pressures. The various gas laws that we have learnt establish the relationship among pressure, temperature, and volume occupied by a certain number of moles of a gas. But air is a mixture of various gases. So how do we know the pressure of a particular gas in the mixture? In 1807, John Dalton studied the pressure exerted by a mixture of non-reacting gases enclosed in a vessel. Based on these studies, he formulated the law of partial pressures. According to Dalton's law of partial pressures, the total pressure exerted by a mixture of two or more non-reacting gases enclosed in a vessel at a given temperature is equal to the sum of the partial pressures exerted by individual gases, that is, the pressure which these gases would exert if they were enclosed separately in that vessel at the same temperature. To understand this law, let us consider three vessels of the same volume at the same temperature. Let the first vessel be enclosed with A moles of hydrogen exerting a pressure of 0.30 bar, and the second vessel be enclosed with B moles of oxygen at the same temperature exerting a pressure of 0.45 bar. Now, if we put both hydrogen and oxygen gases in the third vessel, the total pressure exerted by hydrogen and oxygen in the third vessel would be partial pressure of hydrogen plus partial pressure of oxygen. That is, the total pressure P total is equal to 0.30 bar plus 0.45 bar, which is equal to 0.75 bar. Generally, Dalton's law of partial pressures can be written mathematically as P total is equal to P1 plus P2 plus P3 plus and so on at constant temperature and volume, where P total is the total pressure exerted by the mixture of gases and P1, P2, P3, etc. are partial pressures of individual gases 1, 2, and 3 respectively. Let us now calculate the partial pressure exerted by each gas from the ideal gas equation. Consider a mixture of three gases 1, 2, and 3 enclosed in a container of volume V at temperature T, exerting partial pressures P1, P2, and P3 respectively. Now, by applying the ideal gas equation, the partial pressure of gas 1, that is P1, is equal to N1 RT divided by V. Partial pressure of gas 2, that is P2, is equal to N2 RT divided by V. And partial pressure of gas 3, that is P3, is equal to N3 RT divided by V, where N1, N2, and N3 are the number of moles of the three gases. According to Dalton's law of partial pressures, total pressure exerted by the mixture of gases P total is equal to P1 plus P2 plus P3. On substituting the values of P1, P2 and P3, we get P total equals to N1 RT divided by V plus N2 RT divided by V plus N3 RT divided by V. On simplifying, we get P total is equal to N1 plus N2 plus N3 multiplied by RT divided by V. On dividing P1 by P total, we get P1 by P total equal to N1 divided by N1 plus N2 plus N3. Here, RT and V get cancelled. Therefore, P1 by P total is equal to N1 divided by N, where N is equal to N1 plus N2 plus N3, or total number of moles. We know that N1 by N is equal to X1, where X1 is mole fraction of gas 1. For a mixture of gases, the mole fraction can be defined as the ratio of number of moles of an individual gas to the total number of moles of all the gases present in a mixture. On substituting the values, we get P1 divided by P total is equal to X1. This equation can be written as P1 is equal to X1 multiplied by P total. Similarly, for other two gases, we can express partial pressures as P2 equals X2 multiplied by P total and P3 equals X3 multiplied by P total. Thus, a general equation can be expressed as Pi equals Xi multiplied by P total, where Pi and Xi are the partial pressure and mole fraction of ith gas respectively. Thus, if the total pressure of a mixture of gases is known and the mole fraction of the gas is known, then the equation Pi equals Xi multiplied by P total is used to calculate the pressure exerted by an individual gas. Dalton's law of partial pressures is useful in calculating the pressure of the dry gas collected over water by the downward displacement in the laboratory. As we know that a gas collected over water is saturated with water vapor, it is said to be a moist gas. The total pressure exerted by a moist gas is equal to the sum of the partial pressures of the dry gas and water vapor respectively. The pressure exerted by water vapor, which is in equilibrium with water at constant temperature, is called aqueous tension. If the pressure of dry gas and the moist gas are represented as P and P, and the partial pressure due to water vapor, commonly called aqueous tension, can be expressed as P dash, then, by Dalton's law of partial pressures, the total pressure exerted by a moist gas, that is, P is equal to the partial pressure of the dry gas, P, plus partial pressure of the water vapor, P dash. By rewriting the equation, we get the partial pressure of dry gas P is equal to total pressure of moist gas P minus aqueous tension P dash. You have now reached the end of this module. In this module, you learned that the total pressure exerted by a mixture of two or more non-reacting gases is equal to the sum of the partial pressures of individual gases. The partial pressure of a gas in a mixture is the product of its mole fraction and total pressure of the mixture of gases. Dalton's law of partial pressures is useful in calculating the pressure of the dry gas collected over water by downward displacement in the laboratory.